Welcome everybody to S50B. We're going to be talking about quad trees today. We're going to code from scratch a quad tree implementation suitable for your game project. We're going to do it in 2D. And the reason why this is going to work in 2D is because we don't really have any vertical component to our world. So we don't need to worry about like jumping over a pillar or something like that. Maybe we can add support for that later. It's also a lot easier to just think about things in 2D to begin with, rather than worrying about all 3 dimensions at the same time. So let's first sketch out how a quad tree works. So basically, a quad tree, the 3D version of it is called an octree. The quad tree, when you insert something into the world, it splits the world into quadrants. Then if you insert something else into that quadrant gets split into 4 quadrants, and if you put something here, it splits it into quadrants, and so on and so forth. So you'll have areas that have lots of dots in them. If you put something here, nothing happens. You put something here, it'll split into quadrants. This has, I guess, what we call a threshold of 1. So in other words, anytime you exceed the threshold, you subdivide the region. So if you put a second person into this region here, you subdivide. Now, in practice, this can be a problem, because like if you have 2 dots that are like right next to each other, then it'll subdivide and it'll subdivide and it'll like subdivide. You can actually create quite a deep quad tree just from 2 things being very close to each other. So it's common, you can have a threshold of 3 or whatever. Now, the downside of that is that anytime you do like a array cast or something like that, if you have a threshold of 1, you only have to check the 1 person that's in your zone. If you have 3 people in there, a threshold of 3, you have to basically check the line against all 3, which isn't the end of the world. It's not the biggest deal. But there is a order n, raycast versus a order log n raycast. And so there's kind of a trade-off versus how deep you want your quad tree to go versus, having to just test possibly 1 line against a lot of objects in the same area. So that's a tunable parameter. So this is a parameter that you can tune and get different, performance. You turn it up, turn it down, see what you got. Are they fractals? I mean, they're recursive data structures. Every quad tree is a quad tree, right? Every leaf of a quad tree, like this is a quad tree over here. This area over here is a quad tree, so it's a recursive data structure. So we typically use recursion to iterate through it. Okay, now we're going to do something a little bit different this time. The last time I gave a lecture on quad trees, we were just inserting dots. And this time we're going to be inserting a rectangle. Okay, the reason for this is because your project this semester involves a lot of rectangles. And these are AABBs, axis-aligned bounding boxes, where they are rectangles that exactly parallel the x-axis and that's not very parallel, is it? And the y-axis, right? I can draw a vertical line, there we go. And so because of this, it has some nice properties. We don't have to worry about them like rotating and having some weird cases where they're like extending this way or something like that. But with an AABB, there is a possibility it gets split, right? And so if we split it, then what we're going to do is we're going to clip the each one of the boxes is going to get clipped into potentially 4 boxes. And then each of these is going to get inserted into the respective subtrees. So the original box, we have a vector of boxes, right? We have a vector of the objects in the world that are all rectangles, essentially. They're 3D, but they're essentially rectangles. So we've got a vector of these things. And so each one of these things will have an index, right? Like 1, 2, 3, etc. And so even after we clip these guys will still be referring to the same box, like box 4. And so we need to insert a rectangle, and then that rectangle can get subdivided, but we still need to pass in the index into the vector where the original vector is, where the original rectangle is, because we're going to do things like we're going to have a puzzle where you have to like connect a power source to a thing. We connect it, it lights up, and then we'll connect that power source to another thing, and that lights up. And so we're going to need to be able to get at those rectangles so that we can light them up and record if they're powered or not powered. So that when we do another trace line from there, we can solve the puzzle that is going to be the essence of the fun of this game. So, well, at the end of the day, the player is going to be in the game. They're going to shoot a ray, and then that ray will either hit something or not. And if it hits something, then that thing is going to be attached to the power source, essentially. And so we need to be able to generate a quadtree, and then we need to be able to traverse the quadtree. So traverse the quadtree to find out what's at this point. Boom. Rectangle 4. What's at this point? Nothing. Right? So there's two things we need to do. One is called point contents, the actions we can do on a quadtree. The actions we can do on the quadtree. Well, the first one is build, right? We need to be able to build a quadtree given a vector of boxes containing, sizes of rectangles in the world. You need to be able to construct the quadtree using those rectangles. You need to be able to do what's called a point contents test, which says point contents, which says at this point we are inside of rectangle 4. At this point we are inside of nothing. Okay, it's open here. And it's interesting that it removes that one and the S at the same time. Okay. And then here, we need to be able to do a trace line. Okay. Or a line trace, same thing. Where you can shoot, you can do a hit scan weapon. And we're going to need that for shooting the monsters and for shooting the terrain. And so basically a monster can probably attach itself to one of these nodes in the quadtree. And then when you do a line trace, we'll check both against the terrain and against the monsters as well. We don't need the monsters to subdivide the world. Presumably, we're not going to have too many of them, and so that's not something we're going to optimize for. We're going to optimize for making it fast. Like if you've got a warehouse full of boxes, what we want is the ability to very quickly shoot and be like, this is the point of impact there, without having to do an order N check against every box in the warehouse. Instead of having to test 1 million boxes, the quadtree will let us find the point of impact very quickly. Okay? You guys understand conceptually what we're getting at here? You guys got this? Ready to see some code? Just can't wait for the code. This will be fun. Yeah. It's a lot more fun when your professor codes it than you, right? Unless, Bruce, do you want to code this for us? So we're going to need a rectangle class, and usually a rectangle class is usually held in most graphics programs as a center point and a half width and a half height. I'm not going to do it that way because I have a suspicion it'll be easier for us if we have the edge, the corner points, because when we're going to clip these things and make 4 of them, having the corner points handily available seems more useful than having the center point. Okay, so we are going to need, and we'll do this in double space. We'll have x minimum, x, we'll just initialize these to 0, so x maximum, y minimum, and y maximum. Another way you could do it is have the bottom left corner and then a width and a height. Again, because we're going to be clipping these guys, I suspect this approach is probably going to make our life the easiest. You can sort of use those 3 systems interchangeably. You can always go from one to the other. Like if you want to find what the midpoint is, you just average the min and the max. You average the y min and the max. You probably have to do a little bit of checking to make sure the minimum is not greater than the maximum. But I am not going to do that right now. So what kind of functions should we have on a rectangle? Like what kind of questions would you want to ask a rectangle? What do you think? Raylib does it by center point. Yeah, like I said, it's pretty common in the graphics world. But get size functions cover between get size. Yeah, in fact, we can actually just add a function called get center point, so that if we have a bunch of rectangles, we can just call that and then put them into ArrayLib that way. So we could have a double get. We can do a pair of doubles, I guess. Maybe we want to have a point class. What do you guys think? And then we can have a point for minimum and maximum. Okay. Then we can have a function called get, that'll return a point called get center point. Center point, I don't know. And then that one will return a new point, which we don't even have to cast it to it, where it is min.x plus max.x divided by 2. Parentheses around that. And then min.y, max.y, like that. So I'll look right to you guys. So if we have a rectangle and you want to get the center point of it, because that's how ArrayLib does it, it uses the center point and the half width and the half height probably. Then if we average together a minimum or a maximum, we average together a minimum or maximum. Should be good. You guys cool with that? All right. Are you a parent? I am. Yeah, thanks for asking. Oh, do you mean in the rectangle class? Okay, so we also should get the half width and half height, which we could also return as a point technically. Get half sizes. I don't like these names. And then that one could be return point center equals get center point. And so our half width, do you guys understand what I mean by half width? So the way that rectangles are usually represented in graphics programming is they're held the point here. And then this is 1/2 the width. And this is 1/2 the height. So it's called the half width and the half height. You could hold the entire width and you could hold the entire height, but then you have to divide by 2 a lot. And it's usually easier to multiply by 2 than divide by 2. And there's other reasons as well. You do that. So that is correct. Very good, Raymond. So it is, so our half sizes is going to be return max x minus center x and max y minus center y. And thank you to the IDE for adding an extra parentheses for me. Never change. Okay. So that. If it's overlapping in another rectangle, that's a good one. So because these are AABBs, it's actually a fairly simple check to see if you are overlapping. And you can do so with a Boolean is overlapping with a const rect r. Sure, why not? Okay. And so if rectangle testing, rectangle intersections. Basically, you've got a bunch of different ways that rectangles can kind of overlap. The main thing is you want to see if there is a dividing plane between either of the rectangles. Okay, and if you can find space between any of the rectangles, they don't overlap. So basically, if you have a rectangle over here, you can draw a line between them. And so that's called the overlapping planes method of doing intersection testing. And so basically this will, so we say if the if our minimum x is greater than their maximum x. If our minimum x is greater than their maximum x. So if this is us over here, and this is them over here, our minimum x value is bigger than their maximum, right? This is this is us and this is them. So if r.max.x is less than our min x, that means there's a dividing plane between them. Does that make sense? If our smallest is bigger than their biggest, then we do not touch. Makes sense? And we do this for just each of the different axes, and we're done. All right. So if our smallest is bigger than their biggest, then we return false. We do not overlap. Y, and we're going to p this a bunch of times. So if their minimum is bigger than our maximum, we return false. Right, same thing, just in reverse. If their smallest is bigger than our biggest, there's a plane between them. We don't overlap. And then we do the same for y. Again, this is why we're doing 2D instead of 3D, because it's just one less D you got to worry about. And then if there are no dividing planes that can be drawn, we are in fact touching. Okay. So for this case here, our maximum is bigger than their minimum, so there's no dividing plane. Their minimum is less than our maximum, so there's no dividing plane. Let's see, our minimum x is less than their maximum x, and our maximum x is, wait a second. Yeah, their minimum, yeah. So our minimum is smaller than their maximum. Their minimum is smaller than our maximum for x. Then for y, our minimum is smaller than their maximum, and their minimum is smaller than our maximum. So they do overlap. Okay. I think. We should probably test this. Okay, so we got that. You kind of go cross-eyed, when you look at it for a while. Okay, so we got a Rect class. Now we need to, let's test it first. Let's test this. So we're going to make a Rect called get, because, get Rect, right? And get is going to have, it's going to go from 0, 0 to 10, 10. Let's just do a very simple square, right? And is a 10 by 10 square. If I don't have dad jokes, like I don't even know what I can do, Megan. I think the universe would end. Okay. So we also need point contents, right? Like we also need to say if a point is within. And so we can just say is overlapping for a point. Also const point p. It's an intersection point rectangle intersection test. Point intersection test. And then this one is a rect intersection test. Okay. And so your basic primitives, whenever you do overlapping and intersections, are points, rectangles, lines, and circles, and convex holes. Rectangles, rectangle intersections easy. Circle intersections easy. It gets a little bit more tricky. You have to kind of look up the answers on Google when you get into convex hole / circle intersection. Okay. Do maths. Yeah. Megan does not do mom jokes. That's fine. Okay. Okay. So if the point is between, so if p dot x, so the point's x is less than our minimum, or their x value is greater than our maximum x, return false. Right. So if we have a rectangle and the point's off to the left or off to the right, return false. Do the same for y. We do this all in one line, but I find that when teaching, it's usually better to split things down, break things down a little bit. Does that make sense? So if we're doing a rectangle point intersection, if their x value, here is our minimum x, right? Here's our max x. So if their x value is to the left of our minimum, or if their x value is to the right of our maximum, false. It's not touching. Likewise, if they are above our maximum y, out. And we have minimum y here, out. And if it's not any of those things, that means it's inside. Okay. And let's pretend the handwriting's readable. Okay, so, but I mean, like, just visually that makes sense, right? Like, it's too far to the left, too far to the right, too far up, too far down. Right. Let's test it. Let's make sure that this works. Okay, so we've got a 10 by 10 rectangle. This rectangle starts at 0, 0, so we got a Cartesian coordinate system. And we've got the bottom left corner here is 0, 0. Top right corner here is 10, 10. Little square out of this. Okay. We can do some tests. Let's see if 5, 5 is within. Let's make a rectangle that goes from, I don't know, 6, 4 to 20, 20 or something. Let's see if we get the right numbers out of these things. So we got a point. Let's see if 0.55 is inside of the rectangle. Technically square. So point P, 0.55. So C out, bool alpha, get, fine, I won't call it get Rect anymore, fine. Call it R. Okay, so R dot is overlapping P. Right, so thank you, ID, never change. Okay, so compile this, and it is in fact true. Okay, so now let's move the point out. Ooh, 5. Ooh, that's a bug. Now it filled in 0 for us, and 0. Like it actually turns out that that was correct. But let's try this again. This is why you need to check multiple values. So let's see if 55 is within our square, and the answer is nope. Good. And then let's check the other one just in case we have a copy paste error. 550, nope, great. Let's try 29. 29 is inside. Okay, we're good to go. Check yourself before you wreck yourself. That's exactly right. That is timeless advice. Okay, so that looks fine. Okay, so let's see if another rectangle overlaps it. So let's have Rect check. And check is going to go from, what did we say, 6.4 to 2020. So check yourself before you wreck yourself. So this is check over here, and 6.4 to 2020. All right, and we're going to see if R is overlapping with check. And it is. Cool. So then let's move it a little bit east. So it's at 64. It is no longer overlapping. Let's move it up a little bit. I don't think that's mathematically possible, but there you go. Let's just move it up a little bit. Let's move it to 14, 16, whatever. It's not overlapping. Cool. What if it's 1, 1? It overlaps. Cool. All right. So always make sure you test your code, right? It's really important to make sure that your numbers are good. All right, so we got a rectangle class. We've got maybe we could do a line intersection test. That's also probably pretty important. We do a line, we could do a ray. Those are not exactly the same thing because a ray has an origin. All right, when you shoot a bullet in a game, there's an origin point and then a direction. So let's add ray to this. Okay, so we'll have struct ray because we're using raylib, right? So we need array struct. This is named after Sean Raymond Alexander. Okay, so we're going to have a point that is the origin of the ray. Do we care if the minimum is greater than the maximum? We kind of do, but I'm not spending class time doing it right now because we got a lot to go through right now. But yeah, technically we should be doing this properly using a class because we have an invariant, right? Anytime you have an invariant, minimum must be less than or equal to the maximum. Anytime you have an invariant, you need a private section, and you need to have gatekeepers, right? That will verify that you're not screwing things up. As it is, we're just going to let it break because we got things to do. Okay, we got places to go, and so if we break it, we break it. All right. So let's just to do proper class design. Whatever. Okay. All right. So we got an origin for the ray, and then we've got a direction, right? So we have this can also be represented as it's technically a vector 2D using vec2 equals point. Vec2 direction. Okay. So it's still the point class. Do you guys know you can do that? It's still the point class, but we're just going to call it a vec2 because it looks really weird for direction to be a point. You know what I mean? Kind of. It's a direction. A direction's not a point. It's not a location. It's a direction. So I'm just renaming it to be a two-dimensional vector. It's just an alias. It's a type alias. You can also do type def. It goes the other way. Type def point b vec2 type def. If I could, I'm blaming my keyboard for that one. Okay, same thing. Type def. This is C, by the way, and this is C++. Use the C++ version. Okay. You have no problem with height being stored as a point. Did I? Yes, you are correct. See, the center point's a point, but the half sizes. Yes, you're right. This should be a vector 2. How about that? There we go. Right. This is. Yeah. Okay, no, you're right. Like it's sort of like a philosophical thing at a certain point. We could have called all these guys vec2s, I guess. All right, so we got a point. We got an origin. They're both points, but okay. No more vec3. It's 0.3. Never calling it a vec2 again. Just a 0.2. So much more typing. So much speed. Yeah. Okay, so we got a ray, and the ray has a point and it has a direction. It commits evil with direction and magnitude. So what we need is Raymond. Very good, very good. What we need is a intersection test for the rectangle, I guess. That's all we need. And this is how we're going to do hit scan weapons, right? Right? You shoot, there's an origin, and you want to see if a ray hits you, right? So, which one do I want to copy? Point ray. And it's Y2Y and P. And this will be a ray rect intersection test. Ray. Okay. Fine. We'll call it Mond. There we go. Okay. Okay, and so let's see. Okay. So we got a point. All right. So if the point is within the rectangle, we hit, right? So first of all, if is overlapping. All right, we'll just call this R. Okay. Wait, that's confusing sometimes. Ray. There we go. Okay, so if is overlapping ray dot origin, then return true. So if the center point, close parentheses. If the origin of the ray is inside of the rectangle, then we have a hit. Easy. Caught in 4K, missing parentheses. Yeah. All right. So that's simple. And then the other thing we need to do is we need to use algebra. Okay. So we've got a point. Let's go in this direction. Array. And this is usually it's held as a normalized vector. Right? And then we've got this here. And this is x min, x max, y min, y max. Okay. So we can figure out the point of intersection here by using, if we convert this into line slope equation, it'd be pretty easy. Let's see if there is a, so t represents how far along until we get to x min. So that's based on the direction. So first of all, we have to check for a miss, right? So if we're this way, I don't know if we actually have to. If we get a t of negative, if we get a negative t, that means it's this way. So t is time, essentially. It's what we call it in the biz. And it's how far we need to extend this unit vector, how many times we have to go in this direction until we hit x minimum. So we know that we're outside of the rectangle also, which makes things easier, so we don't have to worry about like hitting the right side first or left of it, that kind of stuff. And so we can take the x component of this, right? We take the x component of the direction vector. If it's 0, then we are moving north-south, and we'll never hit this, right? So, the biz t time. Okay. So if it is 0, then we're only traveling the vertical axis. Shooting array. Oh, you already have code. Raise that at. Do you have this? Are you using line intercept form, or are you using this version, which is like the parametric line equation? So there's slope intercept form, right? Which is what they teach in algebra and what I've used before in my earlier classes. But you really want to be using what's called parametric line equation. Which has a point and a direction, a unit vector. Ray, oh, you already have all the code done. Yes, you were using slope intercept form. Okay. Yeah. So, well, you got the code for that. So we will just see. This is to do for Megan. Okay. Actually, there's one other thing, which is like if ray dot direction equals 0, 0, return false. So if it goes nowhere, then and we're outside of the rectangle, it does not hit. So that's a simple test for really initializer lists cannot be used. I can find point. Really vector. No. Doing a comparison. It is not generating the double equals operator for us. Should... Radar direction is a vector 2. That's a vector 2. It should have a double equals operator defined on it. What am I missing here? Const vec2 dir is equal to ray dot direction. Copy it out. Yes. Yeah, the method needed to be const. Okay. Anyway, we don't have any type aliasing anymore anyway. Okay, so so ray dot direction. That's fine. Okay. Equals nope, it doesn't like that. Okay, that's fine. Cool. Normally, C++ will generate an equality operator for those sorts of things, but it's interesting that it's not. Yeah. Okay. So yeah, if we hit 0, 0, then returns false. All right. So next up, let's return true. Let Megan do this because we want to move on to Quadtree. Oh, you already have the code. You have it up on. Yeah, it's close. You have it in slope intercept form, but yeah, basically, fine. I'll do it. All right. So, test against x minimum and x maximum. Okay. How far till x min and x max. All right. So if we have the direction x component, if direction dot x vector is equal to a dot. If dir.x is 0, then we just skip over to the vertical testing. So, okay, so our point is currently at origin. I'll just alias this out as well. 32.origin is equal to a dot. If so, it's going to be x minimum. Let's see, distance time to x min. So it's going to be, the distance is, the horizontal distance is x minimum dot x minimum dot x minus origin dot x. That's how far the thing is away from us. And we need to divide this by direction dot x. And so double t is equal to how far it is away divided by direction dot x. If t is less than 0, then it's on the wrong side. And it can't hit, at least the minimum. Okay, so if t is positive, then that's how far it is away. Okay, so t is less than 0. Do nothing else. So if t is negative, it's going to be on this side of the ray. If t is positive, we want to know how many unit vectors we have to move to get to this spot here. So we're going to take our origin and multiply t times our direction vector, and that'll give us the point we end at. So like let's say that we're here, right? And it's 3, t is equal to 3, right? So if t equals 3, right, because we computed this is the distance based on how far you move, so it'll be that many things away. If t is 3, then this point here is equal to the origin times the direction, plus the direction, origin plus the direction times time. Okay, so our starting point, we move 1, we move 2, we move 3, that's our ending point. And if that ending point is between y min and y max in the y direction, then we have a hit. Okay. So so the hit point is equal to the origin plus the direction times time. And then if the hit points y is greater than or equal to our minimum y, and the hit points y is less than or equal to our maximum y, then we have successfully hit the rectangle. Okay. And need a multiply operator on you. Return x times t, y times So if you have a vector and you multiply it by 5, each individual component multiplies by 5. And there you go. All right. And so if that is correct, we have that, and we also need a plus operator. Haven't even gone to quadtrees yet. Okay. Okay, so if you add 2 points together, you just add the individual components together. 3, 3 plus 5, 5 is 8, 8. Okay. So now all of that math is out of our way. And then we're going to have to copy and paste this like 4 times. 3 more times. Because you have to handle xmin, xmax, ymin, ymax. And it's pretty much going to be copy and paste, except these will be max x, min y, max y. And then this will switch when you plug in y here, you have to check x here. Okay. Let's move on to quadtrees. So that is Rect intersection testing. Okay. But basically that's your basic idea. If you have a horizontal array here, like here, the unit vector here, it's 1, 0. This guy's at 10, 10, and the x minimum over here is at 20, then t is going to be equal to 10, right? Because if x min is at 20 and we're at 10, and we're at 10, then it is 20 units away from us. And since this length is 1 here, it's 20 away. So we have to add the direction vector 10 times to our origin. Start with our origin, direction times 10 over and over again. Repeated addition is multiplication. That's our hit location right here. And then if that location is between whatever our minimum value for min and our maximum value, or our maximum value for y is, then we've hit the rectangle. Okay, Megan, you got that? In our entire Quadtree lecture, we're starting quadtrees. Damn straight. In fact, let me split these 2 videos into 2 because some people are probably going to want to actually just jump right in on quadtrees on this. So this video is now titled Setting Up Points, Rectangles, Rays, Intersection Testing to get ready for quadtrees. There you go.